Good, how are you?
Good. When do you start your class? It's in January sometime?
Yeah.
When in January, do you know?
Around the 15th,
Okay.
somewhere around
So
there.
a couple of months from now. And you don't yet know whether you're going to start with pre-calc or trig?
We start with trig first.
You do? Okay. All right. Well, we will want to make sure we do at least 2 or 3 sessions on trig before you start your class. It'll just be very helpful to you to have a little bit of a head start. It'll make more sense. Have you had any trig at all in your life? Little bits?
I had a little bit 2 years ago when I took geometry, but
Okay.
that was
They tend to, these days, they give a little bit of trig in algebra 2, a little bit more in geometry, and then the whole course in trig pre-calc. Today, since we still got a couple of months, there's a couple of subjects that I think we probably should cover. One is solving radical equations. And I think we've really kind of done this, but let's just give you a refresher. Would I solve that? That means the cube root of x.
You would add 4 to both sides,
Okay.
and then you would cube it.
So x equals what?
64.
All right. A little tougher one. Yeah, let me not pass over any here that are really good ones to do. Well, let's do just this one here. Equations with 2 radicals in them. What do I do here?
You take everything to the second power, is it?
Yeah, that's what we want to do, is square everything, but we don't want to do it yet. Notice that if we do it now, we're going to have a middle term. In other words, we're not going to eliminate the radical sign if we square it right now. But what if we take the minus 2x to the other side? Now, I can square both sides and not have a radical sign. When I square both sides, what do I have?
You just have 3x plus 2 equals 4x.
Yep. And now x equals 2. Here's the problem if I try to square both sides before moving that over. In other words, if I square this side, okay, here's my answer. 3x plus 2 minus 4 square root of x square root of 3x plus 2, that's the middle term, plus 4x. That's what I would get.
Okay.
Notice that I still have my radicals because I don't get rid of them. Now, I can solve this by moving everything to the right, squaring both sides again, and dealing with that. But you can see that that would be much, much harder to do. In other words, solving it this way is going to involve a whole lot more algebra. Whereas if I merely take this to the other side first and then square both sides, I get the solution almost immediately. Let's look at a radical equation like the following. What now?
Let's square both sides.
Okay, after I square the left side, what do I have?
The left side you have x squared plus 16.
No. That's the biggest single mistake made in algebra by everybody, is squaring this and coming up with a squared plus 1. That is not the answer.
Oh, I forgot to expand it.
Exactly. In other words, when you square something, you have to FOIL it. So
Yeah.
you're multiplying x minus 4 times x minus 4. What's that give us?
X squared minus 8x plus 16.
Good. What do I get when I square the right?
2x.
Okay, now what do we have? How am I going to solve for x?
You subtract 2x from both sides, and then you just do short trinomial. That would be...
Try to factor it. We have factors of 16 that add to the number 10. Let's go through factoring again. If there's one skill you're going to need, it's factoring all the way through all of your math. Okay? So what does this quadratic factor into? I'm not sure how you've learned. Let me teach you my method.
Is it?
First step, separate the x squared. Second step, determine both signs. What do both signs have to be here?
What?
What do both signs have to be? In other words, I want to figure out that sign, the plus or minus, and that sign. That's my step 2.
They both have to be negative.
Correct. That's the only way that we can produce a positive 16 and a negative 10x.
Is it 8 and 2?
I'm sorry, what?
Is it 8 and 2?
It is 8 and 2. In other words,
I just had the multiplication and adding parts mixed up. Like I thought you had to add to get 16s, multiply to get 10.
The third step is to find factors of 16 that either add or subtract. If that's a positive, they have to add to this number. If that's a negative, they have to subtract to that number. Okay? And since that's equal to 0, what are my solutions?
Positive 8, positive 2.
Check both solutions, make sure they work. Second one doesn't work, does it?
No.
That's an extraneous solution. In other words, whenever you have radicals in an equation, you're always very likely to have extraneous solutions. In other words, here's what, if you have a typical quadratic like this, you come up with 2 solutions by factoring it, and both solutions are almost always good. You rarely come up with extraneous solutions. However, you have logs involved, if you have absolute values involved, or if you have radicals involved. Those three things. Or trig functions, sine, cosine, tangent. You frequently do have an extraneous solution. And whenever you're solving equations that have one of those in them, always check both equations to make sure that they work. You don't have to so much on just a polynomial like this, because you rarely come up with extraneous solutions. You might say, well, what is an extraneous solution? Well, why do they happen? It's because when you get to this step, where I say x minus 8 times x minus 2 equals 0, that doesn't mean that both x minus 8 and x minus 2 have to equal 0. It just means one of them does. There's no way you can multiply two things together and get 0 unless one of them is 0. So I come up with these two possibilities, x equal 2 or x equal 8, but they don't have to both be correct. Just only one of them has to be. And in this case, the 2 doesn't work. And we're left with just one. Let me do another factoring one just to illustrate something. Factor this. First step.
X minus 4, x plus 3.
X minus 4 and x what?
Plus 3.
Okay. Pretty good. Yeah, let me not use some big number like that. Hold on a second. I got to think of two factors that are doing what I want them to do. Okay, here we go.
X minus 7, x plus 3.
All right. Looks like you're pretty good at factoring, at least when this coefficient is 1. Now, factoring really becomes problematic when this coefficient is not 1, if it's some number greater than 1. Then factoring is more trial and error. When it's a easy factoring like the ones we've just been doing, then there's not a lot of trial and error. It's just using the methodology. How do I solve this?
Would you take everything to the 5th power?
To the what?
5th power?
2/5. Why 2/5?
Because then both the numerator and the denominator become 10.
Yeah, and then I'm left with x. The goal is to get x. Okay. Now, what is 32 to the 2/5 power equal to? How do I do that without a calculator?
Doesn't it just become a radical?
No. Usually when you see problems like this, they're always going to convert to a whole number. If it's anything other than a whole number, then you wouldn't be able to do it without a calculator. But this particular problem you can do quite easily without a calculator. This is the 5th root, and then we're going to square that answer. That's what 2/5 as an exponent means. What's the 5th root of 32? You may not know it, but it's 2. 2 times 2 times 2 times 2 times 2 is 32. Okay? So now we take the fifth root of 32, which is 2, and square it. So the answer is 4. And like I said, when you get these kind of problems like, is this equal to?
3.
How much?
3.
What's the cube root of 27?
3.
But then you got to square it.
9.
Okay. All right, we're going to take it up a notch here.
First, you would square everything.
Okay. Left side is what?
2x plus 1 6.
That's the easy one. What's the right side?
X squared plus 10 6 x
Good.
plus 10 6.
Got to square that.
Oh. 25 over 30.
Over 36. Mm-hmm. And now it solves, that's a quadratic. You're just going to combine everything and then factor it. Okay. How would I proceed here? What would be the next best step?
I would just multiply everything by 36.
I love
Get rid of.
Yes, get rid of your denominators immediately. So we have 72x plus 6 equals, and you have to multiply every single term by that. And this is becomes 60x plus 25. And now we have something that looks a lot more manageable. I'm going to gather everything on one side. We still have a quadratic. So we're going to have 36x squared minus 12x plus 19. It's a strange number. In other words, there are no factors of 19 other than 19 and 1. So this is not going to be easy to factor. I cannot even take a greatest common factor out of that to reduce it. And it's probably, if I have a chance of factoring it, wow, there's no way. There's no way I'm ever producing that as a middle term having minus 19 and minus 1, which is what my numbers have to be. Therefore, how do I solve this?
You'd have to multiply 19 by 36 and then find the.
No, if I have a quadratic that cannot be factored in the normal way, in other words, I can't find any integer factors, then I got to use the quadratic formula. What's the general quadratic formula? What's the rest of it?
Plus or minus. Is it 4?
It's the square root of b squared minus 4ac all over 2a. Well, in our problem, what's a, b, and c? A is what?
A is 36.
36, correct. B is what?
12.
Minus 12.
That's right.
Not because it's minus B, but B is minus 12. And C is plus 19. In other words, you have to include the sign when you're figuring out what these are. So my solution to this quadratic is going to be minus b, which turns into plus 12, plus or minus the square root of 144 minus 4 times 36 times 19. We can see that that is a negative number. So we are going to have nothing but complex solutions. In other words, once you use the quadratic formula, this is your answer, but the key part of this answer is the discriminant. This is the discriminant, b squared minus 4ac. Well, in our case, that's 144 minus that product of those three numbers. That's clearly greater than 144. And so this is a huge negative number. And that you can't take the square root of a negative number unless you use complex numbers. So I'm going to end up with two complex answers. Only complex, no real.
Are complex numbers just the same thing as imaginary numbers?
Yes, sorry. Yeah, the only difference is a complex number in standard format is a plus bi. In other words, y equals some a plus bi. So, in other words, if I have 2 plus 3i as a solution, that is in standard format. If I have 2 plus 3i over 7 as a solution, that's not in standard format. If I wanted to put that in standard format, I'd have to break it up into two fractions. It's 2/7 plus 3/7 I. And this is A and this is B. A and B are always real, but A is the real part of the answer and B is the coefficient of the imaginary part. But that's what A and B are, is they're real numbers, but B is the coefficient of the imaginary part. All right, there's one other type of radical equation that is tricky. What should I do here? In other words, when you have an equation that has two radicals in it and a number, we had an equation that had two radicals in it before, but there was no number. So I could put each on one side of the equation, square both sides, and get rid of the radicals all in one step. What happens if I square both sides here?
Since there's like an imaginary I, wouldn't it?
No? Well, not yet. Not that I know of. In other words, I don't know that yet. But this involves a process of whittling down the two radical signs to one only, and then isolating it and squaring both sides again. So remember, I'm squaring both sides. So what's the right side become?
25 plus x squared.
Hold on. You were doing these perfect here just a minute ago. When I square a plus b, in other words, it doesn't matter what a is or what b is. That's always going to square to this. Okay? if I square a minus b, it's almost the same answer. The only difference is the middle has the negative sign, but the last still is plus b squared. Okay? It makes a lot of sense to memorize these. I know that you can FOIL them. In other words, if you don't have these memorized, you can go through the process and FOIL them. But when you're doing math, there are so many times where you have to square a binomial term that rather than foiling it, you save a whole bunch of time by memorizing this. So I'm dealing with the bottom one. So the first term is this number squared. What's the next term?
5x.
No, I have to multiply 2 times 5 times square root of x. So that's 2 times 5 times root x. That's the middle term. Or 10 root x. And then finally, the last term is this thing squared, which is just x. Okay? With me?
It's hard to use.
Well, memorize this. And it doesn't matter whether it's a minus b or a plus b. If it's a plus b, this just is a plus sign. So if I'm squaring anything like this, first term is going to be a squared, that's 25. The middle term is going to be that times 2. That's how I get that. 2 times 5 is 10, times root x is 10 root x. And finally, the last term is always a plus whatever this thing is squared. Well, if I square the square root of x, I get x. Okay? So, where that leaves me is I still have a radical equation that I have to solve. Only it's a little easier now because I only have one radical sign. Okay, what's the next step? First of all, you see how we get to here?
Yeah.
Okay, now what?
Would you just subtract x plus 5 from both sides?
All right. Well, clearly the x's cancel, right? I mean, let's start there. And now, what's the goal? The goal is to isolate that right there. How can we get that isolated? Because once we get that isolated, then I can square both sides and solve. But I can't do any squaring until I get rid of everything except that. I could even handle the 10 being next to it, but I won't need to. Okay, so let's take this 10x to the other side. 10 root x. Let's bring the 5 to this side. So that's what I've got now. Okay. Next step.
Could you change the radical into the fraction form?
Well, we're trying to isolate that. We got to do one more thing before we isolate that.
Divide both sides by 10?
Yeah. So now I have square root of x equals 2. Now what?
Square it.
Square both sides. X equals 4. Okay. Now, let's check to make sure that that is a solution to this thing. Well, x equals 4. This is what we started with. When x equals 4, this is square root of 9, so that's 3. And when x equals 4, that's 2, so we have 3 equals 3. So it works. Most of the time when you only get one solution, it's not going to be extraneous. It's going to work. There are some equations that do not have a solution, and yet they will solve for one, and when you go to plug it in and check it, it doesn't work. But most of the time, if you only come up with one solution, you can be pretty sure that it works. It's not going to be, in other words, if you come up with two solutions, say I come up with x equal 4 and x equal minus 3, well, now by all means, you have to check both of them, because we're looking at radicals. Anytime you have radicals, you have possibilities of extraneous solutions. Okay. See if I can find anything else that looks interesting. You know, let's do one more of those. Again, this is going to be tough, not because we necessarily have two radicals, but we have two radicals and then we have a number over here that's not a radical. In other words, I can't isolate that on one side, isolate that on the other side, and square both sides. I could if this wasn't a 4. If this was a 0, I could do that. But if it's a number, there's no way to do it. So what's my first step?
Subtract one of the radicals from both sides.
Okay, let's do that. I'll just pick one at random. Now it looks a little bit like what we just did. Now what?
Could you square everything?
Uh-huh. Again, let's square that using what we just learned.
16 minus 8, and then in a radical 3x minus 5 plus 3x minus 5.
Good. What's our next step going to be? Or what's our goal going to be from this point in?
To get rid of the radical.
Right, but we're going to do that by isolating that. In other words, we're going to move everything else on the other side of the equation, isolate that, and then square both sides again. So a lot of times when you have two radicals in a problem, you have to do this process twice. In other words, the first step got rid of one radical only. We got it down from two radicals to one radical here. Okay, and let's take this to the left. So that'll give me 8 root 3x minus 5. And I have x over here, and let's see, I have 16 minus 9. That is plus 7. So that's what I get when I gather everything together. Unless I made a mistake in my math. I don't think so. Okay, now what?
Divide both sides by 8.
Yeah, I can do that.
Or you could subtract 7 from both sides to get 1.
No, you can't do that. This 8 is multiplying, not being added. If this was 8 plus this, then I could do that. But it's not. The only question I have here is, do I divide both sides by 8 first before I square everything? I don't have to. In other words, even though I said my goal is to isolate that, once I get it in this form, I can actually square it. What do I get when I square the left side?
64 times 3x minus 5.
Right, like that. What do I get when I square the right side?
X squared plus 49.
No. This is an a plus b quantity squared. Don't leave out the middle term. Yes, the middle term is extremely important. In other words, you'll never get it right if you leave out that middle term. It's never the same as the other. Okay? And now I have a quadratic. In other words, I have nothing but x squared, x, and a number. That's going to produce more x, more numbers. I'm going to gather everything together, solve it, come up with two solutions. Quadratics almost always give you two solutions, and then try both of them and make sure they both work. Okay? I'm not going to go through that process just because we're dealing with big numbers here and they're not going to factor particularly easy. So I don't want to waste 10 minutes, both of our time, trying to factor this thing after I gather everything together. Notice my middle term alone is going to be minus like 178x. My number is going to be minus 289 or something. So it won't be easy to factor once we do gather everything and put it in proper quadratic format. But it's always doable using the quadratic. In other words, it doesn't matter. I can give you a quadratic like this. Okay? Now, there's no way I'm factoring that in a normal way, but I can always solve it by plugging it into the quadratic formula. Let's say I had this problem right here. Okay? The one I have circled. What's A?
3.
What's B?
-1.
Good. And what's C?
-19.
Right. A lot of people will say B is minus X. B is only the coefficient of the X term. It does not include the X. All right. I think that's as hard as you're going to be faced with, where you have two radical signs and you have to eliminate one at a time by doing what we did. All right, let's see. We are about ready to start trig. There is another major chapter of precalc that you're going to have to know, and that's conic sections. You know what I mean by conic sections?
No.
Was that a no?
Yeah, it was a no.
Okay. Parabolas, circles, ellipses, and hyperbolas. Have you ever studied those?
We did parabolas.
Okay. Parabolas might look like this, but in the context of conic sections, they can also look like that. Whereas they don't have to be functions. Circles are the easiest one. Ellipses will either be elongated like that, or they will be vertical like this. And hyperbolas tend to look kind of like this. Okay? And these shapes have great meaning in real life. All of the planets in our solar system either follow an elliptical path around the sun or they follow a hyperbolic path. Comets will follow hyperbolic paths. So the math of conic sections is extremely important for determining the motion of the planets in our solar system. And each of these four conic sections has its own type function. In other words, the function of a circle is x squared plus y squared equals r squared. The function of an ellipse is x squared over a squared plus y squared over b squared equals 1. And a function for hyperbola would be x squared over a squared minus y squared over b squared equals 1. Does any of that look familiar?
No.
Definitely something we need to cover then. But it might make sense for us to wait on that. In other words, if we know you're starting with trig, then I say we go right to trig. We're going to have, I don't know, 5, 6 sessions before you start back to class. We can get a lot done in trig in those 5, 6 sessions. It'll make your trig class so much easier. Conic sections, it would take us in tutoring probably 3 full sessions, maybe 4, to adequately cover conic sections in the way that they're going to teach it to you next year. In other words, you will get this, but you might not get it until May or June or April or sometime like that. So let's not do conic sections now. Let's start with trig. Trig starts right here. Uh-huh. What does this SOH mean?
Sine, which is opposite over hypotenuse.
And the CAH?
Cosine, adjacent over hypotenuse.
And the TOA?
Tangent, opposite over adjacent.
This applies on right triangles only. What is the sine of theta? We always take trig functions of angles to get ratios. Okay. What's the sine of theta?
3/4.
Opposite over hypotenuse.
Oh, I wasn't looking at.
Longest side of a right triangle is always the hypotenuse. Hypotenuse is always opposite the right angle. So it's 3 divided by 5. What is the cosine of theta?
4/5.
And what is the tangent of theta?
3/4.
Now there are 3 other trig functions. These are the 3. What kind of calculator do you use?
Do you want me to go grab it?
I just thought if you knew. Is it a TI-84, TI-83, TI-Inspire?
I think it might be an 83, but I do know it has this sine, cosine, tangent functions.
Right. In other words, if it's a TI-84 or less, you're only going to have 3 buttons on there that are trig functions, and that's sine, cosine, and tangent. There are 3 other trig functions: secant, cosecant, and cotangent.
I know mine has that as well.
Ah, you might have an Inspire then. The Inspire, when you bring up when you push the button that says trig, it gives you a choice of all 6 trig functions. But
Yeah.
regardless, that's not going to really help you that much. What you need to remember is each of those 3 other functions are the reciprocal of each of these. What do you suppose the reciprocal of tangent is?
Cosine?
Here's the other 3.
Oh. It's
Cotangent. Okay, that's the simplest, most straightforward one to know. So the tangent of theta is always equal to 1 over the cotangent of theta. Okay? Now, placing the other 2 is the tricky part. Trig is all about memory. So if you want to take math that is very, very memory dependent, trig is going to be it, more so than any other math that you've ever taken. And memorizing this stuff, there's a lot of little techniques you can use. Okay? I know that one of these other 2 functions goes with sine and the other one goes with cosecant, or cosine rather. The trick is there is exactly 1 co in every reciprocal relationship. So it has to be like that. Notice there's the co in this pair. There's the co in this pair. And there's the co in that pair. Okay? So the only thing you really have to memorize is what goes with tangent. And that's pretty easy. I mean, to remember. Cotangent figures to go with tangent. And so the only thing we have to remember is, does secant go with sine or does secant go with cosine? And if you remember this thing about the cos, you won't ever have a problem with it. Now, there are 6 reciprocal relationships. This is 3 of them. Well, the other 3 are just the reverse. In other words, if sine is 1 over cosecant, then cosecant is 1 over sine. And if cosine is 1 over secant, then secant must be 1 over cosine. So you don't really have to remember these. You can always figure these out from the first 3. So here are 6 of the most fundamental things that you're going to have to memorize in trig. But the only one you really have to memorize is that one. You can figure out the other 5 based on the little tips that I've given you. Okay? And basically what this means is that if the sine is 1/2, then the cosecant must be 2. In other words, if I tell you the sine of theta equals 1/2, then you can tell me, therefore, the cosecant of theta would have to equal its reciprocal, 2 over 1. Okay? Now, those 6 are the very first 6 things you're going to have to memorize in trig. Let's see, we got 5 minutes. There's something else I was going to talk to you about regarding trig, and I just lost my train of thought. These 2 triangles are the foundation of trig, believe it or not. These 2 triangles that you've been getting ever since Algebra 1. They've been talking to you about a 45-45 right triangle and a 30-60 right triangle. Now, what you have to memorize is the dimensions of this triangle. Okay? Now this is what I call my unit dimensions. And I call them, in other words, this could just as easily be 2, 4, 2 root 3. Okay? I call this a unit special triangle because the side opposite the smallest angle is 1. Well, over here, the smallest angle is 45 degrees. That side's 1, that side's 1, that side's root 2. Okay? If you can recreate both of these triangles from memory, and you want to be able to, trust me, then you can do your trig functions of all of your common angles in the first quadrant. And what do I mean by the first quadrant? Have you ever seen the unit circle?
Yeah.
Quadrants are numbered counterclockwise. So this is the first quadrant. This is 90 degrees. This is 180 degrees. This is 270. And this is back to 360. Okay? So when I say an angle in the first quadrant, I mean either 30, 45, or 60, not 27. They want you to memorize all of the common ones. And by memorizing, I mean they want you to know the sine of 30, the sine of 45, the sine of 60, and the sine of 90, and for that matter, the sine of 0. All 5 of those are really in the first quadrant. And let's talk about the 3 in the middle. These are the key ones. What's the sine of 30 based on my triangle?
1/2.
Yes. What's the sine of 45 based on my triangle?
1/√2.
And what's the sine of 60 based on my triangle?
√3/2.
They're going to want you to memorize the 3 answers to these angles for all 6 trig functions. Sine, cosine, tangent, secant, cosecant, and cotangent. Okay? Now, that might seem hard because there's 3 things, there's 6 trig functions, so they want you to memorize 18 things. But notice that I can get every answer from these 2 triangles. So the only really thing that you have to memorize are these 2 triangles. If I give you these 2 triangles, then you're going to be able to give me the trig function of any trig function. What have I said? What's the tangent of 45 degrees?
It would be 1/1.
Correct. What's the cosine of 45 degrees?
1/2 square root of 2.
Is there anything wrong with that answer?
The radical's on the bottom.
How do we radicalize it? Or how do we rationalize it? In other words, the radical being on the bottom means we have an irrational denominator. Not a good answer. Go ahead.
We'd have to multiply the top and the bottom by square root of 2.
Giving you?
Square root of 2/2.
Right. So that's actually the correct answer. Same exact number. If you put both of these that I have circled in a calculator, you'll get the same exact number. But this one's been rationalized. This one has not. So we don't really want to give answers that have radicals in the denominator. But even still, what is the secant of 60 degrees?
One over square root of 3 divided by 2?
First of all, what's the reciprocal of secant? What?
Cosine.
Right. So what's the cosine of 60?
1 over 2.
What's the secant of 60?
1
2 over 1, the reciprocal. In other words, if the cosine of 60 is equal to 1 over 2, that means, by definition, the secant of 60, which is the reciprocal of cosine, is the reciprocal of that, 2 over 1. So as long as you know your reciprocal relationships, now you have everything you need to answer all 6 trig functions for any of these angles. And that's where we'll stop for now. Okay? We'll go on and study the unit circle next time.
Okay.
All right, Isa. Have a good week. I'll talk to you next Friday.
Alright, see ya.